So this session will be handled by will be going to handle by Mr. Jai Ganesh. So no need of any introduction about him. He already handled our session, and he is going to deliver a talk on large language models with hands-on today. Over to you, Jay. Happy learning,
Yes.
participants.
Yeah. Thank you, ma'am. Thank you so much, ma'am. So very good evening to one and all present here. And this is Jay. Already, I already was handled a couple of days before I was handled the sessions. I hope you're aware of me. Just give me a second. I'll adjust my mic. Just give me a second. Yeah, I'm back. Um, so the part of my session is all about LLM models. Yeah, of course, LLM models, and I hope you already walked through some LLMs, like how the LLMs looks like, and what is the usage of the LLMs, and how the tokenization is works, or what is a transformer, encoder, and the decoder architectures, and attention mechanisms, and QKV parameters, and all about like how the BERT models actually works. I hope that you already walked through this kind
Jay,
of.
Jay, sorry to disturb. We could not see the slide. Are you
Sorry,
sharing?
ma'am. Yeah, about to share now. Yeah, a minute. So today I'm going to begin with fine-tuning the LLMs. So it's a quite advanced content actually. Let me share the screen, overall screen. Yeah, I hope it is visible. Yes. So the my part of session is I told you before, like I'm going to talk about a fine tuning of an LLMs. So LLMs, I hope so. Like you have experienced from Hugging Face some various LLMs like Distilbert and Robata and Falcon. Llama models. So might of some of the models you might have been worked on, and you might be so curious to understand how to fine tune these LLMs based on your project specifications. So I have no you have known about it. Let me show you some before I'm walking through the source codes presentation. I'll show you some Hugging Face. So in the Hugging Face, you know about how what all the models are present. So this is an AI community where you can able to walk around the multiple models with respect to text classification, token classification, table question and answering. For example, I will be taking here text classification. If you take the text classifications, a lot of prime models are available in the market, and in Hugging Face, lakhs of models are available here, of course. And then, of course, if you wanted to use a Distilbert for your text classification problem statement, you can just pick it and you can integrate on top of your source code, and you can able to do it by using this model kind of snippets and everything. And if you wanted to experience, I love this product, from the core to the core. So if you wanted to experience like how the model is actually works, you can use this inference provider to know on everything. So now you might have a questions in your mind. Okay, sir. So these all the LLMs are available. Of course, we welcome it because these are all the powerful LLM models, and so trained with a lot of parameters and everything. Okay, fine. So how can we take these LLMs and how can I able to fine tune these models for my problem statement? Okay, so there is a different type of fine tunings are there. Okay, I'll tell you everything one by one. So you might have this question. Okay, you have a set of data sets now. So for the generation model you have a set of data, and now you wanted to train that model, I mean llama model, if you take it in the sense you wanted to fine tune with your what is it, your organization data or your college data, your academics data, or something else. You wanted to fine tune it, and you wanted to enhance the knowledge of the fine LLM model in order to utilize it in the going forward. Okay, in order to do this, how we can able to do it? It's not easy generally what we have done before in the CNN architecture using some of the pre-trained LLMs, right, which is 16, 19, and what is that, inception, exception, ResNet models and all. So likewise, how can we able to fine tune this model to adopt for your project specific? That's what we're going to see it right here. It's almost the same concept. So transfer learning, you might have been experienced a concept called a transfer learning, right? It's almost the same concept, but here we will be telling in the name of fine tuning. in the generative AI era, we'll be spelling it out in the name of fine tuning. Okay, so I hope you all so curious to know about it, how to fine tune and how to this works and everything. So first thing is I have to step it around on LoRa and the Q-LoRa adaptation techniques. So these are all the two concepts, which helps us in order to fine tune our complex large language models. So large language models in the sense, BERT model, if you take it, is a 110 million parameter BERT based model, whereas if you take a like a BERT large model, it would be like a 360 million parameters. Whereas if you step around, apart from SLM models, if you step around LLMs like a Falcon 1 billion parameters, Lava 7 billion parameters, and Mistral 7 billion parameters. Likewise, ample amount of models are available in the market, and everything is like a quite larger parameters. And fine tuning these parameter, do you think like is that much of easy now to work with? Of course it's not. So that's what we have, some kind of techniques, named called LoRa and Q LoRa. So LoRa in the sense nothing but it is a low rank adoption, and the Q LoRa is nothing but it's a quantized low rank adoption. So let's understand step by step. So now if you see the first step, it's a fully fine tuning. So what is the meaning of fully fine tuning? Consider I'm having one LLM model. So that LLM model is like a 3 billion parameters. So consider like how large your model is, 3 billion parameters. Okay, so now you wanted to fine tune your model, fully fine tune in the sense you have to fine tune all the parameters with respect to your data. Okay, for example, your LLM, already you have some LLM, so that LLM is already trained with some finance data, some law data, some comprehensive data and everything. Now you are taking that data, so now you are taking that LLM which was trained with the 3 billion parameters. Now you have some medical data in your hand. You wanted to fine tune this model by using your medical data. So now what will happen? Okay, if you fine tune the fully model, of course it's not as easy as we think. So what is a complex, sir? What is the problem? Why you are making us so scary for fully fine tuning? It's nothing but because if you fine tune your all the 3 billion parameters, it is not that much easy. Reason is nothing but we have a we have a lot of accelerated hardware acceleration issues. We don't have that much of hardware accelerations. Okay, so what is an hardware acceleration? In the sense like, you will be having a downstreaming tasks like, in order to find you like a 3 billion parameter model, in order to find you a 3 billion parameter model, of course you should require like, 8 GB of RAM, sorry, 8 GB of graphics card minimum. I'm saying minimum 8 GB of graphics card, 16 GB of RAM, and also you require some amount of quite amount of storages and everything in order to perform this in a betterment way. Okay, 3 billion parameters. Okay, this is not, of course, it's not an easy amount. Actually, this is not easy configuration not to find on it. And with respect to this 8 GB, will it you will be having a good fine tuning? Of course it will not be. Reason is nothing but, think about it, you are fine tuning your entire model, you're fine tuning your entire 3 billion parameter. What will happen in the sense, there was some concept called the what is it, catastrophic forgetting. What is the meaning of catastrophic forgetting? So think about one concept. So consider this is Jay, and I have already trained with a lot of, what is that, AI concepts, machine learning and deep learning concepts and everything. So now I have lakhs of neurons within me, and I have all the lakhs of neurons is trained on completely machine learning and deep learning concepts. Now you are taking some, what is that, some military data or some vehicle data, and you're fine tuning me, and you're fine tuning completely each and every neurons you're trying to fine tune me. But but what happens, sometimes the weight will be updated on top of the existing knowledge. Okay, sometimes what will happen in the sense, with respect to the earlier knowledge, it will be adding on top of it. So machine learning knowledge, deep learning knowledge, I know, on top of it I'll be adding like a finance knowledge. It's fine, not a big deal. But it will not happen, of course, when you're fine tuning your model for the over the time period. So 100 epochs, 200 epochs, 300 epochs, what will happen in the sense, your model will fit into like a catastrophic forgetting. Catastrophic forgetting is nothing but you are forgetting, you are making your model to forget the previous data. So making your model to forget the previous data and fine tuning a model with the newer data, it's of course not helpful at all. Am I right? Because why we are using that LLM? So we have that LLM, it's having a previous knowledge. Through that previous knowledge, you are adding other knowledge on top of the LLM in order to have a new predictions or the new generations or new classification or something else you are trying to do. But with the help of this concept, of course, your model is not that much helpful. So what is the challenges in the fully parameter fine tuning? Hardware acceleration issues. There is a lot of downstreaming tasks like a model monitoring, inferencing, RAM and GPU, and storaging and updating the weights requires a lot of memory within your hardware, and also the RAM memory it's require a hard, and which limits of fine tuning to larger CPUs. And also all the weights gets updated repeatedly over for the multiple epochs. Cause of that, we will be getting the issue of catastrophic forgetting. This is why we'll be having an issue with the fully fine tuning. And now you can see this picture, right? This is an optimizer state, and this is an adapters, and this is a base model. So this is your base model. Consider this is your llama model, so llama 7 billion parameter model, and this model is fine tuned. This model will be like a 7 billion parameter, and each parameter will be having like a 16 bit transformer, 16 bits data. So each and every parameters will be having the data knowledge of like a point 1 1 2 3 4 5 6. Likewise 16 bit it will be having the floating point. So now you will be having like a fully fine tuned when you're doing a fully fine tuned with the optimizer state, and you are adapting those data with the base model parameters. Okay, so now what is the logic we are applying on top of the LoRa here? If you see the LoRa, you can see that I have a LoRa and I have a base model with 16-bit transformers. That means I'll be taking the same llama model with the 3 billion parameters. This 3 billion parameters model, okay, 3 billion parameters model, I'm going to fine tune it, but I'm not going to do the entire fully fine tuning. Instead, I have some data, optimizer state. I have some data. Okay, I'm updating my model with the few adapters, with the less amount of adapters. Okay, these are the adapter data I'm going to integrate with my base model to make my model to understand with the new knowledge what it was earlier doesn't aware of it. This is what low rank adaptation. Okay, so low rank adoption is nothing but like we're going to take a base model, and we're going to fine tune that base model by using some adapters. That adapters is not fine tuning your entire base model parameters. Instead, we are creating a separate adapters like some amount of 1% or 2% of your model parameters we are taking, and we are adapting them. This is called LoRa. And what about the Q LoRa? It is a LoRa 2.0. Okay, it's a version of 2.0 of a LoRa. So what does the meaning? It's a Q LoRa. It's a quantized low rank adoption. So now you have a 16-bit per transformers here, and you can able to see here 4-bit transformer. That means when I'm using like a model for example llama of 7 billion parameter, 3 billion parameters model, that 3 billion parameters, every parameters with a 16-bit transformers. But here I'm telling to my model, just make a 4-bit model, 4-bit transformer. Let's make it as a 4-bit transformer model, so that all my data, all my parameters, all the 3 billion parameters, instead of holding like a 0.12345 6 up to 16 bits, we are making them to 4 bits. That means 0 to 0.1234. This is the maximum bits we're going to hold it on top of this transformer. You get it right what I'm trying to say now. Cause of that, so okay sir, what it doesn't make. So how this will pull? Of course, this makes a lot of huge impacts on top of your training. The memory wise and learning wise, and as well as the storage wise, it will be make a huge impact. I'll show you in a separate slide. So this is a thought about what is a fully fine tuning and a LoRa, and as well as a Q LoRa. So types of fine tuning. So we have a different types of fine tuning: fully parameter fine tuning, domain specific fine tuning, and the task specific fine tuning. So what is a domain specific fine tuning? And also we can say it as a what is that specifically you're taking some LLM model, and you're fine tuning that particular LLM model with respect to specific domains. So specific domains in the sense some AI domain, or else you're taking some law domain, or you're taking like a medical domain. Likewise, you're taking that LLM and you're fine tuning that. That is what we can call it as a domain specific fine tuning. And also we can name it as a task specific fine tuning. So what is a task specific? In the sense, to finish a particular task. So classification is a one of a task, and generating some amount of data, right? That is a one task. Likewise, if you wanted to fine tune your model with respect to some specific task, in the sense, that is what we can make it as a task specific fine tuning. In a task itself, we have a three different tasks. One is like a instruction fine tuning, and another one is like what is that chain of thought fine tuning, and the third one is like a multitask fine tuning. So what does it these three topics mean? In the sense, I can show you with the Hugging Face model here. T5 small, some model it is actually, exactly I don't know. Let me pick this one. This image is supposed to be slowed. I don't know why is it not loading. T5 small. Flat small. Yes, so this is about three types of fine tuning I told you, right? Apart from this, instruction fine tuning. Instruction fine tuning is nothing but please answer the following question: what is the boiling point of nitrogen? It will tell you like 320 degree Fahrenheit or 480 Fahrenheit. Likewise, this will be giving you some amount of information, straightforward information. What is your name? My name is Jay. What you are doing? I'm working as a lead AI architect. So what is your overall experience? 12 years experience. So likewise, this is an instruction fine tuning. I'll be taking my model and I'm fine tuning my model in such a direction. This is called instruction fine tuning and the chain of thought in the sense you can see this question like the cafeteria has 23 apples and if they use like a 20 for lunch and bought six more, how many apples do they have? Now, if you ask this question to my model in the sense what your model will understand, it will started to understand. It is a thought actually. It's a chain of thought. So in order to answer for this question, it needs to understand what is the overall apples and how many of them was used and how many of them are left and what is the remaining apple. So likewise it needs to do some math behind of it through the thoughts. So this is called thought of fine tuning. Okay, and another one is like a multitask fine tuning. If you see this question like can Geoffrey Hinton have a conversation with the George Washington? So let's forget about this question, so I'll ask other question instead of this. So is APJ Abdul Kalam had a dinner with Jawaharlal Nehru. So now if you ask this question, what your model will do? So your model will understand this question and it will check Dr. APJ Abdul Kalam born at the time of 1976 or 1956 or something else, and Jawaharlal born at the time of 1854 something else, and he died at the time of 1950. So there is no chances of they having a dinner among themselves. This is what your model does. This is called the multitask. You are giving a question. Your model will be thinking in the different direction based on the different task, and it is trying to connect them. This is called multitask instruction fine tuning. Okay, so this is all about nothing but this is all our is all is a part of our fine tuning mechanism. So instruction fine tuning, chain of thought fine tuning, and multitask fine tuning, everything is like a part of our fine tuning mechanism, and everything is a part of our chat gpt usages because you have this knowledge right now. Of course you will be asking this question. You will be asking like a chat gpt like what is the difference between gpt-4 and gpt-5. This is like a multitask, so it needs to gather gpt-4 gpt-5 and it needs to merge. And the chain of thought in the sense you will be taking some aptitude questions or you will be taking some summary of your some of the books and you will be giving it to the model and you are asking it to summarize. That is a chain of thought. And you will be asking about like what is the recent nvidia launches in the last week, so your model will say you some information. That's about instruction fine tuning. Okay, so these are all the different type of fine tunings are there. So we must have this knowledge when you are approaching your model for the different level of fine tuning. So I have a couple of examples of hands-on codes. One is for instruction fine tuning. It's like a more like a classification problem statement. On the other hand, I have other problem statement is all about like a fine tuning like based on what is that chain of thought fine tuning. Okay, let's explore one by one. Now going back to the slide again. So how LoRa stands different? Of course, instead of updating the weights directly, we track changes. That means downstreaming tasks. So downstreaming task is not applicable here because LoRa will not take all the parameters of the model and it will not going to update all the weights of your models. Of course, right? That's what LoRa stands different. It will be taking a few amount of parameters and it's going to find out. Consider like you have a 100 parameters. You have a Llama model 100 parameters that already this Llama model is fine tuned on finance data, medical data, and as well as some common what else we can take. Some law data. Okay, now what I'm going to do in the sense recently there was some disease came in the market is a corona. So now I wanted to fine tune my model with this corona data set. So what I'll be doing in the sense out of 100 parameters, 40 parameters is trained with the medical data. So what I have to do in the sense when I wanted to fine tune, I'll be fine tuning only that 40 parameters. And if you ask me that all the 40 parameters you will find in, of course I will not do it. Out of 40 I'll be taking 20 parameters or 10 parameters only. I'll fine tune the model in order to make my model to understand what is corona and what is the treatment we can able to approach and what are all the things we can able to advise for this particular corona treatment. So this is what I'll be doing. So I will not touch other parameters like a law parameters. I will not touch, and I will not touch other what is that social related information. I will not touch those parameters. This is what your LoRa will do. Instead of fine tuning all the parameters, it takes only the specific parameters. What are the parameters needs to be fine tuned, that parameter it will pick and it will fine tune those parameters and then then it'll update the models. This is how actually your LoRa stands different. So you can ask me, okay sir, having doing this process, so it will not fit around like a catastrophic forgetting. Of course it will not, right? Because we are not going to find an entire LLMs. I mean, we are not going to find the entire parameters of the model. We are going to find tune only just a 5% or 10 percentage of your model fine tune. We are update 5% of the 10% of the models we are fine tuning it, so that your model will not fit around any catastrophic forgetting. And if it happens forgetting, there was some problem in our fine tuning mechanism. That's what maximum it will not happen. So these weight changes are tracked in two separate and smaller matrices that gets update multiplied together to form a matrix the same size of the matrix of model weight. So what does it mean? So the weight changes are tracked in two matrices. Now you can see this picture. In this picture, I have a LoRa weights. Okay, so I have a LoRa weights and I have a model weights. So LoRa weights is nothing but like, so what is the parameters actually have been changed. Okay, the model weights you can able to see all the 125 parameters, all the 25 parameters I have been in this my model. Now I need to append this data. I need to merge this data in order to have a fine-tuned model weight parameters. Now you can ask me a question. Okay, Jay, you said that like you're going to take a model weights and you're going to find out only the few amount of a LoRa weights, right? So but here if I see all the parameters is considered into the game. So how we are doing it, so 25 and also the 25 parameters here. So when you are merging, of course it will be taking a time process, and it will take your memory, and it takes your storages, and it takes your lot of blah blah blah, right? So how actually this will work, this is nothing but, now if you see that this particular concept, so I'll be having like a original model here, original weight is here, and you can see the other hand I have a two simple matrices. Okay, these two simple matrices is like a array one this is you can able to see in another array. Okay, so I don't have all the 25 matrices, all the 25 pixels right here. So instead what I'm doing in the sense, by using these simple two matrices, I'll be forming this LoRa weight changes. How I will be doing in the sense, by multiplying this one. So this array, this particular cell with this cell, this with one, this one with this one with this one with this, and similar wise this one with this one with this one with this. Likewise we will be forming the same matrices as like it looks like. And you may have think, okay, how this could be effective? Of course, like having the overall weights is different, and multiplying and forming the newer weights is of course different, right? Yes, of course there will be some losses will be there, there will be some less accuracy impacts will be there, of course. But anyway it will not that much impact, it will not make, because if you have this particular two matrices, so we can able to regenerate the entire matrices itself of the way we want. And of course we'll be having some reconstruction loss, we will be having some less in loss in accuracy, but it will not make that amount of impacts. That's what it's trying to say. So this matrix decomposition is a one of a key how it composes. Okay, if you want me to explain better more, consider you have a matrix as like a 500 cross 300. Okay, so now 500 cross 1. Okay, this is 500 cross 1, this is called 1 cross 300. Now by using these two matrices I can able to form that 500 cross 300. This is a logic is all about. Okay, so now I have a original weights, I have all the original weights, and I'm forming I'll be generating this LoRa updated weights through this matrices. I'll be forming the overall weights, and I'm merging them, and I'll be getting the fine tuned weights. This is about actually your low rank adaptation techniques actually works by using the rank, by using these two small matrices with respect to the ranking position. I'll tell you what is a rank and all. Now you can ask me, okay sir, what is a rank which was mentioned right here? Okay, rank is nothing but how effective you are expecting your model to fine tune. So now if I keep a rank as a one, in the sense I'll be having just a one matrices. And if I wanted to have a more accuracy, and if I wanted to have a more accuracy, then I should increase the ranks of my matrices and ranks of my matrix decomposition. Now the changing the rank matrix which helps to increase the accuracy of the model as the trainable QKB parameter increases. This is what. So for example, if you wanted to increase if you wanted to increase the accuracy of your model, you can increase the rank so that you will be getting the higher precision in the weight changes. You can able to reflect it off. Then you can ask me another question. Okay, Jay, at what scenario I should go for lesser rank? At what scenario I should go for the bigger rank? You may have this question in your mind, of course. So I'll answer for it. So before that, I'll conclude this point. So now math equation behind the LoRa weights. Now if you see that This is an equation. Actually, if you see this LoRa and QLoRa, what is that? It's the inversion paper. Actually, this reverse pair, what is the research paper? You can able to see across this particular equation is walking around in and there. And this is a weight new weights which is equal to W plus del W. So what is this weight and del W in the sense? So weight in the sense nothing but it is a overall your model weights. Actually it's actual model weights is represents as a W here. And what is the del weight is represents here, this is a WA into WB. That means that two matrix decomposition, that decomposed matrix is there, right? That is a one matrix, this is another matrix, and you are multiplying them and you are getting the del weights here. Okay, so this is called new weight. Okay, this is how actually we are forming the new weight, and in this below picture you can able to understand better more. So this is my frozen weight. We are not updating any of the model weights, we are not going to update any of the model weights. Instead we are creating two separate adaptation matrices. By using these two adaptation matrices, we will be forming the other matrices, and we are clubbing them together. We are clubbing them together, concatenating them together to have overall weight. Okay, so this is how the overall picture looks like. This is how the overall methodological picture looks like, what I have explained in the mathematical. Okay, this is a equation behind the LoRa weights updates, and how LoRa handles the precision. Now if you see this, you can amaze some informations, of course, right? Rank 1. Okay, this is a 7 billion parameters. Let's take a llama model. So llama model 7 billion parameters, and let's take like a llama 13 billion parameters, llama 70 billion, llama 180 billion parameters. So we have a three different billion parameters we have in the hand. Now I'm taking a rank 1. Okay, so that means 167K, that means 1,67,000 parameters I'm fine tuning as part of 7 billion parameter. That means it's just a 0.00%. Just a 0.00%. You can ask me, so Jay, we are fine tuning like a 1,60,000 parameters right here, but here it reflects 0.001 00. It's not actually 0.00, actually it would be like a 0.001 percentage parameter. So overall it represents with the two precision, it's like a 0% parameters. And if I fine tune the same model with the two rank 2, this will be like a 334K parameters. That means it makes a different impact, 0.01% impact. And whereas if you go for like a 8 rank, it's like a 1 million parameters. If you take a 16 million, 3 million parameters. On the other hand, if you see like a 8,192 rank, if you choose in the sense, it will be fine tuning of like a 1.4 billion parameters of 7 billion parameters, which percentage wise it impacts like just a 19% you are updating your models. You're just updating your model with a 19% of your overall parameters. It's truly, when you're seeing like updating a parameters, finding a parameters, it will not make you amazed like, okay, we are fine tuning the parameters, we're going to get a results out of it. But when you see this result comparison, you can able to understand we are just fine tuning a lesser very very fewer parameters. And you can ask me, okay Jay, did you the real time did you people fine tuning with the rank of 8,190? Of course will not. Maximum will do with like a 1024. This is what I have tried with the maximum rank. So maximum 1024, because the rank increases, your model complexity increases. Your model complexity increases, of course it will be eating GPU capacity, potential, all potentiality also it will increase. So likewise there's a lot of issues will be there in and around. Okay, so this is a like a 2.45 parameters, just a 2.45 percentage of the your model parameter I'm fine tuning on top of it here. Now if you see like a 7 billion, 30 billion, 180 billion, the same kind of results you can able to get it. It's truly a big deal. Fine tuning a parameters, fine tuning a model is not as easy as we think. And even if you fine tune the model, will you get a perfect results? That is also questionable. So how effective you're choosing the rank, how effective you are choosing the alpha, and how effective you are choosing like other parameters, n-log parameters, epoch parameters, and everything. It truly matters on top of fine tuning. Anyway, I'll show you the hands-on so that you have a quite knowledge on top of it. And scenarios, so you have other thoughts like a scenarios where a higher ranks truly helps, like of course a teaching a complex behavior, teaching behavior that contradicts or falls outside the scope of the previous training. That means, consider, as I told before, right? So I have LLM just 100 parameters, just 100 neuron parameters, and these 100 parameters is already trained on law data, medical data, and as well as what is that, some comprehensive data. Okay, now you wanted to fine tune this model with the corona data. Of course there was some medical data is there. Now your model can able to adopt corona informations on top of it to understand what it is and how it is and what is going to actually work. So your model does understand what it is. Okay, so this is called less complex behavior. So that time we can go for like a rank values like a 4, 8, 10, 16, 24. Likewise we can choose the ranks and all, because you don't need to increase the accuracy. So it's not mandatory to increase the rank sizes to increase, because already your model has some similar weights, similar knowledges. But whereas your LLM model is already have like a law data, medical data, and comprehensive data, and suddenly you are taking one data. That data is about a space data, space relevant data. Your model doesn't aware of what data is actually is about. Now, if you fine tune this data with your model, it will be taking it will be taking a more time. It will be require more model weights to changes, and it needs to get adopted based on the space data. And of course, it is a fits on top of its it of course it fits outside the scope of the model. So at the time you have to increase the rank and you have to increase the values in order to fine tune that model, right? So this is what I have mentioned in the scenario. Here's there's a BERT model which trains on the common behavior data. You would like to make the model to generate a diet and a fitness suggestions, since where it is totally contradictory with the existing knowledge. And here increasing the RAM would help to elevate the model accuracy by updating the more parameters. That's what. So this is how where you have to choose the smaller ranks and where you have to choose the higher ranks. If your model is like already have knowledges about a medical and your fine tuning data is also relevant to the existing knowledge, in the sense not a big deal, you can choose with like a ranked 16, 24 kind of proportionality you can go for. Whereas your model doesn't aware of like a space data and you wanted to find it with that data, you have to increase in the rank values like a 8,000 or sorry 1024 or else a 2000 and 4000. Likewise you have to increase the rank values in order to make the metrics complexity to understand your model is about. Okay, so now talk about QLoRa. So quantized LoRa. So what is a quantized? This is a version of LoRa 2.0. Of course, what I mentioned before the same. So QLoRa, which is equal to like a quantized model plus low rank adoption, low rank adopters, and the pre-trained base model. Okay, this pre-trained base model is quantized to 4-bit precision using NF4 or FP4 formats. That means this is a pre-trained model, base model, right? It will be fine-tuned, it will be quantized with the 4-bit precision models using some formal techniques, like a formal techniques called normal float or the float for mechanisms. We will be taking this model to 4-bit. So you can ask me, okay Jay, I will be confused here, so what is a quantized to 4-bit? So now nothing, but I have a llama model which is available in a server. Okay, so now I decided I need to use a llama model for fine tuning it, for fine tuning. As I told before, right, I wanted to use a quantized LLM model instead of using like a actual LLM model. Actual LLM model, each and every parameters is a up to 16-bit float. Okay, it will be like a 16-bit parameters, it will be there. But I wanted to download a model with just a 4-bit parameters, 4-bit or maximum 8-bit. So you can go for this is a quantized model. So I'll be having each parameters, so weight will be having like a 0.1234 or 0.12345678, maximum 8 parameters it will be there. So this is a quantized parameter. So this drastically makes a huge impact on the memory usages and computational cost without significantly degrading the performances. Okay, but people are saying like it will not make the significantly degrading the performance. But in a lot of research papers of the QLoRa paper, if you take and if you study about, they are mentioning the same. You can take the QLoRa model, quantized model, and you can fine tune the model. Of course you will be having the significant results how the actual LLM model will give you the results. And in realistic of course it will not be, am I right? Because there is like a 16-bit and here you're dealing with a 4-bit. Your model loses information, of course it will be losing the information. There was, but in the research paper they are having some proven ideas, they have some proven results. This quantized model will not reducing your reducing your performance of the model evaluations or something else, it will not be. This is what they are saying. But there is no static proofs. But with respect to my knowledge, with respect to my ideology in my organization, we fine tuning with the quantized model. We do faces a lot of performance drops and we do faces a lot of accuracy drops. It will be there, of course it will be there, but the proportionality is little reducible. Like maybe if I have all the 16-bit, in the sense I would have get like 60% accuracy. But if I'm using a quantized model, but I'm getting just a 40% or 38% or something else, of course I have to lose 20% here. Of course I have to lose a 20% here. That 20% is nothing but like in order to optimize, in order to optimize my GPU, in order to optimize my CPU performances. Okay, so and you get the both the benefits, of course, like a memory efficiency since we are quantizing the model, and flexible and a task specific learning. Okay, and how LoRa and QLoRa parameters helps. If you talk, sorry, if you talk about like it scales the contributions of the LoRa adaptation matrices, and alpha determines how much the fine tuning model should impact the new trainable data. There was other parameter, proportionality parameter of rank actually. So what does that mean? In the sense, if you choose the rank, this defines what is a this defines the accuracy of your model. Okay, rank is defines accuracy of your model, accuracy of the data your model which trains on. But what is the alpha? In the sense, how effective your model understood the data. That's what your alpha determines. You mentioned, right, if you choose alpha value is a low value, the base model mostly relies on what it already knows. If you choose like a very less alpha value, if even though if you fine tune a model, it sticks around only with the data, only with the knowledge of what it already has. Okay, but if you stick with the high alpha value, the base model started to influence us more on the new training samples. This is what actually your model is trying to say here. Okay, your base model is like a started to understand what are all the information it's actually trained on, and then your traits and the models and everything is started to influence on top of it. This is what your alpha values are determined. So I can show you some examples so that you will have a better knowledge on top of it, and how the actual equation will be looks like. This is how the equation looks like. So w dash, that means a new weights which is equal to the model weights, the concreted, I mean the what is it, the frozen model weights plus alpha divided by r. Alpha in the sense of scale values divided by the ranks b and a. So this is like decomposed matrices. Okay, this keeps a variance of update stable and prevents the low rank matrices from dominating the original weights too aggressively. So if you use this proportionality, this if this is for proportionality, it makes sure your alpha factor makes sure it is not affecting your original weights, it is not affecting your original weights, and the weights are updating too reliably based on the newer data, and it makes your model to influence with the current amount of fine-tuned data also. Okay, and also the common values, what kind of values we can choose, like of course 16, 32, 64, sometimes higher, of course, if you choose for. And a small task you can go for like alpha equal to 16, and the rank you must choose 8. And for the complex task you can choose like a 32 and 32 or 128, and the rank must be 16 or 64, but in real time sometimes higher also. Okay, this is a proportionality where you wanted to choose like your alpha parameters completely depends on your rank, because if you choose a rank it's a 8, you have to choose a alpha is a 16 and to the double of that. If you choose like a alpha equal to rank is a 64, your alpha must be like a 128, because accuracy increases, adaptations also must be increases. Okay, so if you're choosing like a rank is a 64 and you're focusing on increasing the model accuracy, but you fail to adopt your model along with the newer update weights, your model will fail. Like for example, if you're choosing like alpha equal to 32 but your rank is like a 64, your model focusing on increasing the accuracy, but your alpha parameter is the one which makes sure weights are updating properly, and what are all the weights needs to be updated, that makes shows the alpha parameter. That alpha will makes your model to collapse if you fail to choose a proper alpha value. This is a prime parameters of the LoRa and QLoRa, and apart we have some more we'll see in the source code developed discussed dis- while discussing in the source codes. Okay, so any doubts on top of this presentation? Maybe when I'm showing the source code, you have a better understanding what I was talking about alpha, what is a rank, and what is a LoRa, and what is a QLoRa, and everything. Okay, let me
Jay
take.
sir,
Yes,
somebody
ma'am.
has asked a query.
Okay, ma'am.
They wanted to know layer-wise processing. Explain the
Layer
fine-tuning with some CNN models. Somebody has asked it like such. Layer wise
Ah,
processing.
so layer-wise processing means, ma'am, actually with respect to this LLM, actually fine-tuning with the some CNN model. No, actually, this is LLM models are actually. So we are taking the LLM model. So we are fine-tuning the LLM model. The fine-tuning a CNN model is a different. That is what a transfer learning technique, right? The transfer learning techniques we'll be doing it, right? That's what we can call it as a fine-tuning of CNN models. Mm, and the layer wise processing, sorry, I lost you. What is layer wise processing? So layer wise processing is all about, we'll be having it, of course we'll be having it when you talk about like what is that transformers. So when you talk about a transformers, you will be having a knowledge about like a layer wise processing. So there it will be there. Actually there also we cannot able to select a layer wise processing. There we will be having a lesser layers like add and normalization layers only we'll be having there, and more or like we'll be having an attention mechanism up there. So layer wise processing, here we have a less influence in generative AI, and the LLMs will not be having a layer wise processing much influenceable. So yes, other
Okay. Okay.
question.
So, participants, do you have any other queries regarding this LLM models discussed by sir? Do you have any queries? Otherwise, sir will go with hands-on. Okay. Okay, sir, you please.
Yes, ma'am. Yeah. So yes, now I can go with the fine-tuning mechanism. So using LoRa and QLoRa, and actually we have other fine-tuning. It's not exactly like a fine-tuning, but it's one of a base fine-tuning. One of a base fine-tuning of your BERT model that also I have. But anyway, since I was covered like a LoRa and QLoRa, I'll finish that concept first. Then I'll take you to. I'll take you another example. Take a BERT model and taking some classification data set and fine tuning our model with that data set by adding additional layers to make your model to understand. Okay, so how we will be seeing it, right? Example, if you see this Hugging Face here, this is a Google model. This model is a what model it is? It's a text generation. This is a text generation model. And now if you see that, and some of them would have done the same. Actually some of them, for example, if you take the text classification, I go for the text classification. This is a digital bird model. This is for like a fine tuned with the text classification. This model is completely tested with the fine text classification. But a digital bird model is nothing but this is just like a, it's like a language model. Digital bird is like a just a language model. Now they have made this model as a text classification model by fine tuning additional data called SST2 data English. This is what they have done. So this is the way I'm going to do. I'm going to take a bird model. On top of this bird model, I'm going to fine tune with my classification data set. Some of the email classification or sentiment classification I'm going to take, and I'll be fine tuning my model. I'm going to make as like this. Okay, so this is also I'll teach you. That is simple fine tuning, of course, when compared to LoRa and QLoRa, but that is not most advisable and most usable in the real time era. Okay, so I'll take you to the code. I of course this is quite interesting and quite complex too. So I have a two parameters. This is a simple, not a simple model. It's a 1 billion parameter. Okay, finding Falcon 1 billion parameter. On the other hand, I have a Llama of 7 billion parameters also. But it's fine tuning your complete model. It's not as easy as we think. Let's see how I have done here. We can have a walk around. So I'll share this source code with you all. Please load it from your end. And if you open it through right here, like if you do open it through my GitHub, it will not open as I have some APIs exposed in this particular source code, so that it will not open here. But when you try to open through Colab, it will open. So I'll show you that also. So I'm going Colab now. So let me take Jayesh19. This is my ID. So here I'm taking into to which one I have to go for. Here. All right. Search. NLP. Oh, sorry, my bad. Yeah, here it is. NLP IATD. I'm choosing right there. I need to turn off my charger. Yes, I did. So here you can see. Where is it? Where is it? Where is
Hello,
it? Where is
sir.
it? Yeah, here it is.
Sorry
Yes.
to interrupt you.
Yes, ma'am. Please, ma'am.
Sir, I'm not able to copy this path.
Mm, okay. A minute, ma'am. Please, ma'am. I'll give it again. Not able to copy it on miss. How it, ma'am? Like this, ma'am. I
Yes, sir.
will paste it again, ma'am. Can you try it now? You can just copy it, ma'am. You can just copy this up to HTTP. Oh, you can't copy the selected. Yes, understood, ma'am. Your problem. I can understand your brain now. I don't know why is not possible. You can't copy the selected text. So you are getting the same, ma'am. So you can't copy the selected text. This is what you're getting.
Okay, sir, please.
Okay. Okay. Put share. Share. Okay. Where it will be. I don't know where it is exactly. Yeah, sir. So this is a chat, right? Actually, this is not a chat. Okay. I don't know exactly. So maybe better you can take my repository itself, ma'am. Instead, I'll tell you like I'll tell my repository itself instead. You can go to my repository. So this is my GitHub Jaish1IN. Okay. So if you go to my repository, ma'am, so you can find a repo name called NLP Okay. So here you can able to see like a NLP So if you go to NLP you can just get in NLP Here you can find transformers and BERT, ma'am. So inside the transformers and BERT, you can find the source code called, you can get inside like a PIF to fine tuning, ma'am. PIF to fine tuning, so parameter efficient fine tuning. Okay, if you go inside the parameter efficient fine tuning, you can find that what is that? The Falcon 1B using LoRa and QLoRa, ma'am. This is a source code, ma'am. So you have to
Okay,
go
sir.
my repository name called NLP Yes, ma'am. Transformers PIF to, ma'am.
Okay, sir.
Yes.
Okay, okay.
Yes, ma'am. Thank you, ma'am. Okay. So now once you have loaded, you can able to find this source code. This is how my source code appeared like this. So first let's start with the code explanation. So now I'm just installing the required packages, transformers, of course, from a Hugging Face, and another one is a data sets. I'm going to import some data sets, and the PIFT, this is my parameter efficient fine tuning mechanism, and accelerate. This is accelerate model to build some model to runs and bits and bytes. Okay, next one is like I'm importing the necessary packages, a torch, and from the transformers to load a tokenizer, to load a model for trainer arguments and the trainer function and the data collator. So this I'll explain you later. And if you see this is a PIFT model, this is a major parameters. This is a major import right here from the parameter efficient fine tuning packages. We are using LoRa configuration, get PIFT model, and a prepare model for k-bit training. These are the three functionalities are very important for LoRa and QLoRa functionality. Okay, now you can see this data set. Now here I'm not loading the data set of from the Hugging Face. If you wanted to use some data set from here, you can choose them also. Okay, instead of like this, use this data set, you can go to here, you can just to copy it, and you can, instead of this data set, you can take this data also. This is your wish, whatever data set you wanted to. But here what I have done in the sense, I manually created some data set on my own manually created some data set. I'm taking a text data set. This is my question. Okay, so what is the capital of France? And answer is a Paris. And what is a who wrote Hamlet? And answer is a William Shakespeare. So what is a question like a what is 2 plus 2? Answer is 4. Likewise, I have my data set, I have my JSON data set. So now I'm going to take my model, I'm going to fine tune my model with this data set. Of course is a lame data set. You don't shout at me on this case. Like this of course is a very base data set. This is for an knowledge share, this is for explanation part. I have kept it here. That's what I told you. You can take any data sets from the Hugging Face. Instead of this data set, you need to replace that data set. That's all you have to do. Okay, so now I have taken this my data set. Now what I'm going to do next one is I could take step to 2. So in step 2, I'm just doing like a, this is a model I have chosen. This is a Falcon 1 billion parameter model. Now I will show you how this model actually looks like. Now this is my model. Okay, this is a model. I'm going to take it from Hugging Face itself, like a Fontcon 1 billion parameter casual decoder model. This is a casual decoder model. Okay, and this is like a trained on 350 billion tokens of refined web datasets. It is made available under the Apache 2 license. Okay, so if you wanted to learn about more about this particular model, you can take a look at it. Here you can able to see the lot amount of interesting information about the models. Okay, so now let me take into the actual content of this code. Okay, now I'm using this model. Okay, now if you wanted to use other models, okay, so what else I can go for? Like you can choose like a tiny llama. So tiny llama with the 1 billion parameter models also is there, you can choose it. So maximum choose like a 1 billion, don't go beyond that, because fine tuning 1 billion itself is a quite hard right here. Okay, so now I'm importing the tokenizer. I hope you all aware of these steps. And also I'm importing the tokenizer. I'm just making the like a padding token as a end of token. So like I'm just making it as a, for example, here you can see what is the capital of France. So here the here the other token is like a just Paris, right? But here I have a 4 5 6 tokens are there, so other 5 tokens are not here, so I will be making it as a end of token, uos. I hope you are aware of this concept. uos. Likewise I will make it in order to make my tokens are equal. Okay, so this is what I'll be doing it here. So that is a maximum, because all the tokenizer doesn't have of this padding tokens and all. That's what we are intentionally telling to my model for a padding. And the next one is like I'm downloading a model here. So auto model. Okay, from here I'm downloading the model called, what is that, Falcon 1 billion model. Now here you can observe a part is like a load in bit 4. Okay, load in bit 4 bit. Okay, load in 4 bit, which is making it as a true. That means I'm telling to my model, download a model with the 4 bit. Okay, with the 4 bit accuracy. So there is a 4 bit parameters. So 4 bit parameter in the sense, all the 1 billion parameters will be downloaded with the maximum bit of 0.1024, maximum 10, sorry, 1234, maximum 4 parameters it will be there. So that means this is how I'm making my model quantized. I'm downloading my model in the quantized format, and I'm torch dictionary like a divide, what is it, data type is of course like a 16 bit data type, the framework data type. And the device map I'm making it as an auto. Now you can see this below. LoRa function prepares a model that was loaded in a 4-bit or 8-bit quantized model. So most weights are integer 6 in 4-bit, compressed to save the GPU memory. And but some parts, layer normalizations or output heads you might have experienced in a transformers, still needs to be in a float 32 or float 16 for training stability. Okay, so most of the internal parameters, the most of the internal weight parameters we'll be converting into 4-bit. So with the help of this function, preparing my model for 4-bit, k-bit in the sense like here I'm making it as a 4-bit training. Then my model I have given here, my model is ready. So now my model is downloaded with the 4-bit quantized model. Now if you wanted to choose like a 8-bit in the sense, you can change it as a 8-bit right here. That's it. Okay, and also if you wanted to download a model with all actual model in the sense, you can make it as a function as a false. If you make it as a function as a false, it will be downloading as a model. So now your QLoRa part, this is about a QLoRa part. Okay, now stepping into LoRa functionality. So LoRa adaptation. So here I'm creating the configuration first. Okay, here I'm creating the configuration or rank. As I told you before, like the increase in the rank, the accuracy will increase. Of course, here I'm keeping our LoRa rank as 8. So LoRa alpha, so scaling factor. The scaling factor I'm making it as a 6. If you have a good alpha, your model will understand. Your model will try to adopt your new trainable parameters along with the previous trained parameters, or else it will not it will it will ensure how much your data supposed to be influenced with the previous data points. Okay, that will be ensuring of that point. The next one is like a target module. So what is the parameter we do focus? Of course, like we have to focus on the attention mechanism in the sense QKV parameters. Okay, you have to focus on QKV parameters. Targeting models is all about QKV values. And the next one is a dropout. I'm mentioning it has a 0.1%. That means like a 10% I'm dropping out. I'm mentioning it here during the time of fine tuning. And the bias, I'm keeping it as an none. I don't want to make any model to be biased at the time, since I'm having a very less rank, less lower, and a less epoch right here. And the task type is like a casual alarm. This is not like a fine tuned LLMs or nothing, but this is not, sorry, no, this is not like a masked LLM. This is like a casual LLM. So masked LLM in the sense nothing but your BERT and SLM models are there. That is a masked LLM technique. This is a task type is nothing but casual LLM. I'll tell you the difference. So what is a masked LLM and what is a casual LLM? So now I defined my configuration. I defined my LoRa configuration. Here I'm making my function out. So now in this function you can able to see get a PIFT model, get parameter efficient model. What is the model I'm going to use? Like this quantized Falcon model. This quantized Falcon model, I'm just giving it here. At what parameters? What is the adapter? This is an adapter. This is the adapter I'm going to add. Now my model is ready. My model, base model plus my LoRa configuration parameters. That means It's here where it is. I have shown, yes. So this is my base model, and now I prepared my adapters. Okay, now I have prepared my adapters. Okay, so now I have prepared my model. Now I need to train my model. So still my model is not trained actually, so I need to train my model. Now you can see this is a tokenizing the data. Okay, here I can see, you can see this a tokenizing the data. So in this tokenizing data, it's nothing but whatever input you are giving, right? We have to tokenize them. Okay, and then only we have to append it, we have to make our model to train on top of that. So to tokenizing, of course, I'm giving the sample text and I'm applying the truncation. Padding, I'm giving it as a maximum length as a padding, and a maximum length of the maximum length I'm giving it as a 128. Okay, so each word will be, 128 length is all about like a maximum length. Okay, so that means here you have just five, four, five, 6 words are there. Okay, maximum 6 words are there. So that means 122 words yet to be padded. Okay, here there is a one word is presence, and that means 127 words are padded. Okay, this is how we are telling to model. Of course, you know how the padding data will be handled by the model and all. I hope you all aware of that knowledge. Now the tokenizing data set is done. Okay, now I'm tokenizing my data set. My tokenization maps is done. Now I'm training my model on top of this new parameters. Of course, here training arguments I have to define. What are all the arguments? First thing is like a output arguments, like this is a dummy. Internally it will be storing that per device training batches. That means each GPU takes 4 samples at once. Okay, if you are giving like 100 data in the sense per each during the each GPU, right, or each and every second, each and every during each batch sizes, it will be taking a 4 samples at a single shot. Okay, so 4 GB in the sense for each GPU will be taking 4 samples at a time for training, and the number of training epochs just making it as a 3 here, but the 3 and all will not help at all. Okay, and a learning rate 0.0002. Of course, I'm making it as a very less, and floating point 16-bit. Yes, I am using like a half precision floating point here. Okay, I'm making it as a half precision floating point. That means like a to save the GPU memory. Okay, generally we'll be keeping it as a 32-bit, but here I'm keeping it as a 16-bit.
I have
So
a
what you can
question
ask
over
me,
here.
you
Sir, I
can,
have a question over here.
yeah, please, sir.
Sir, just now you have told that the text that you are taking, you are tokenizing it, and once
Mhm.
the tokenization is done, so you are not going for embedding part of it.
No, no, sir. Actually, here we are not doing embedding at all. We are just giving the data. So when you are giving into the model, that will take care of the embedding. Of course, these data will be embedded, and then only it will be giving into your model. So when you're fine tuning your model, right, when you are training this model trigger, at the time that data, that token data will be embedded, then it will be giving it to the model. So that's what, like, you will be having like a position embedding and as well as a actual word embedding. This is how your model will do, sir.
Thank you.
Yes, sir. Yeah. So that means here I'm just doing the tokenizing. So I'm just telling to my model my tokenized data is ready. But when you are triggering your model will be having like a, it will be receiving the data in terms of the embeddings, and it will do the embedding. Then it will be taking it for the fine tuning. This is how your model works. Yes. Next one is like a FP16. So what is a FP16 in the sense of float point 16? So here I'm telling to my model, like I told you, I have mentioned it, right? All the parameters we are not converting into 4-bit. So some of the primary layers, some of the attention layers, so we are converting into the 4-bit, and the rest of the some of the functionalities like a normalization layer, some of the output heads, we still keep it as a float 32 or float 16 in order to have a good training stability. So that's what I mentioned here. So you wanted to keep it as a float point as a 16. Yes, of course, I'm telling like a 4.16. So if false in the sense, it will be taken as a float 32, float point as a 32. This is called half precision floating point. Okay, so logging steps is, so each and every each and every steps, right? So within the 3 epochs are there. Each steps, if each epoch 100 step in the sense, at 100 every 10th step, I wanted to log the information. That's what I mentioned as a logging steps. And the next one is a save strategy. No, I'm not having any specific strategies to save on top of this model because I'm not uniquely doing anything right here. So I'm keeping it as a no, and report to none. So I don't want to do any path to log the generate the raw logs or something else. Now, during this process, my model will be training, and you can able to see how my model will be downloading and do kind of things and all right here. Okay. So next part is like a collata. So here data collata. So data collata for language modeling. So now here you can see that here the part of this concept this works around. The data collector takes tokenized sample from your data set and it turns them into the mini batches that model can consume. So now what it will do in the sense, now here the place where we will be doing that embeddings kind of things and all. Okay, the padding the sequences, it padding the sequences and shifting the tokens to align with the actual input and outputs. Likewise, and optionally we will be having like a masking. So what is a masking? It will be doing it here. So during this functionality, I'm just telling to my model what is a learning methodology you wanted to focus on. You know that like a bird will be having a two type of learning parameters. One is a two type of learning techniques. One is like a masked language model, and another one is like a next sentence prediction. Okay, so most of the encoder and decoder will be having the similar technique, but the casual LLMs will be there, right? Casual LLMs will not have a MLMs. Okay, so casual LLMs will not be having a MLM. So that means like a sorry, that will not be having like a masked language model. Instead they will be having like a what is that randomized prediction techniques. That's what I'm specifically mentioning this. So MLM true in the sense this is like a masked language model, fine tune a model with the masked languages. So if you are having this particular text in the sense your model will mask your model will model mask these two data, and it will try to understand what these two data and all. This is what your BERT techniques generally will do. But when you this is that's what I have mentioned right here. But when you go for like a false, this is like a casual language model. So GPT models mostly we can mention it as a casual language model like a GPT Falcon training. Here we are predicting the next word. Here our focus is all about like understanding the overall data is a matters, but it will be trying to understand what is the next word. Okay, what is the next word is all about. That's how your model will be understanding. Okay, so this is a casual language modeling techniques. That's what I'm telling. Like you'll take the tokenization and a data collator for the language model I'm defining right here. So here I'm defining the trainer. So during this place I'm taking my model, I'm defining my training arguments. What are the training arguments I must consider as part of a game? And the next one is a training data set, a tokenized data set I'm giving, and I'm giving my tokenizer. Here I'm giving the data collector. So when I'm triggering this model, when I'm triggering this a trainer, what happens, it takes all your tokens and it will be converting them to embeddings. I mean the what is the input embeddings plus position embeddings. Then it will be convert that embeddings will be fine tuned with on top of your model. How it will be fine tuning? By using like a training argument. So we have given the some set of training argument techniques. That is how by based on that parameter your model is getting trained. So once it is get trained, your model will be ready right there. So now here you can see my model is ready. Model, I'm evaluating my model. Here I'm testing my model with some question. Okay, so now I'm asking what is the capital of France? Okay, I'm asking my model what is the capital of France. Now my model will say like my prompt I'm giving into the tokenizer. So the prompt I will be getting the tokenizer here. That tokenizer I'm giving into my model. Now my fine-tuned model will be generating by taking this input with the maximum new token is like a 30 new token. So maximum token generation for one question is like a 30. Okay, so I'm just limiting it out. And the next one is a do sample. You wanted to sample, yes, of course, true. That means enables a sampling instead of greedy decoding. So what is a greedy decoding? In the sense it's like a always picks a most likely words. So okay, so always choose the most likely words. Now if you choose like a do sample true, okay, so do sample true in the sense it's focusing on the greedy decoding. That means how to say mm, the sky looks like. Okay, here I have a sentence. In order to answer for this particular sentence, in order to predict the next word of this your casual LLM, it will be predicting almost like a 50 to 100 words. It will be predicting like it will be like say like a blue, white, orange, cloudy, green, black clouds, black clouds, beautiful, amazing. Likewise, it will be having like a in its bucket it will be having almost 100 to 200 words it will be there, consider. Okay, so here when I'm giving a do sample equal to true, enabling sampling instead of a greedy. So that means greedy in the sense it'll always pick the most likely word out of this one. It will be picking most likely word. The sky looks like blue. Likewise, it will bring the most likely word based on the percentage. Actually, that I'll tell you later. Okay, what is a sample? What if I'm giving a true? What if I'm picking a true? If I'm picking a true in the sense samples, choose randomness. Here I'm giving to my model, right? Instead of choosing like a most likely words, I'm telling to my model choose randomly. So it will be choosing a beautiful. The sky looks like beautiful. Likewise, it will be picking. Okay, sir, this looks like it's so chaos, no, sir. So how your model defines it? So that is what we'll be having like a top K. So I'm telling to my model limits the sampling to the most 50 most likely next tokens at each steps and pick randomly ones. Instead of generating all the 100, you just limit yourself up to 500 records. Up to 500 records. This is what I'm telling to my model. So now how about I have to pick? How about I have to pick? That's what I mentioned is a top precision. Top precision is a 90%. Instead of fixing fixer of k, instead of have a fixed k, take the smallest set of tokens whose probability sum of 90%. If the top three tokens already cover 90%, only those three will be considered. So that means like I'm telling to my model 90%. So 90% in the sense this will be like a 99%. This will be like 98%. This will be like a 99%. Okay, again it will be considered like a 97%. Likewise it will be there, and some of the values is like a 80%. This is a 80%, and the rest of them is like a decreasing in such a way you consider like a 80, 79, 74. Likewise it will be there. So now your model will consider, since I'm giving is a 90%, since it is getting 80%, it will be taking 90% only from to the cart. Okay, formally now, so even though the 50 samples I have given in the list, it will consider only the top 4 records. Out of this top 4 records, it will take a randomness one. That's what I mentioned as a do sampling. So I'm not using like a greedy decoding here. I'm just mentioning as a sample one. Okay, so this is how your model chooses. And the temperature, of course you know about it. What is the temperature? If your temperature is less than 1, it will be having like a sharper distribution. That means like you can able to get like a relative information, relative data based on how your model has been trained on. And if your values are greater than 1, you will be getting like a sugar code content. That means like a flatter distributions and more randomness you can expect. So sugar coated data and more randomness and more exaggerated content you can expect on top of the models. Okay, now this is how your model will generate an answer for each and every question is all about. Okay, now, okay, sir, now you have done all this. Now my model is predicted. I'm decoding it. Now you can able to say what is the capital of the France. Of course, yeah, my model is predicting is a Paris, and also it is generating some other blah 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 information because I have mentioned as a token as a 30. So it's also generating some nonsense data. I have to limit them off. But my model is predicting as a right answer, of course. And you can ask me, okay, sir, are you sure about it? Is your model is predicting Paris exactly what you trained on with this information? Because it's a very less data. And how do you confident of course I'm telling, right? I'm just showing you a prototype here. Now if you go to this model and if you ask about like your, okay, inference provider is not available. If you ask about this model, what is capital of a France, without fine tuning, your model will of course can able to answer it's a Paris, because your Falcon model is more likely trained on the most common generic data, GK data, so it can have a lot amount of knowledges. But if you fine tune this information with some corona data set, if you fine tune with specifically with some military data set, of course your model can able to understand in the betterment of it. You can understand it, right? What I'm trying to say. This is all about a prototype. That's what I told you the initial time itself. Whenever you find in a model, choose some other data sets. You can just replace this code with your data set. Here my data set is there. You can choose some of the data set on your own NVIDIA data set. You can choose your data blah 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 blah. Here you can just, then some fine tuning is of course required. Don't shout at me at that moment. Okay. Okay, you can take this data and just replace it off. That's it. Okay, I'm just educating you, right? This now I'm going to the point. So now all this point is done. So okay, sir, what will be done? So I wanted to push this model. Some people in the real world scenario, they are pushing the model. Okay, now the model is done. Now if you run this code, it will push the model to your Hugging Face space. Already I have pushed to this model. I will show you for demo now. I have already pushed it. So this is the model. Where is my model? Yeah, this is a model I have pushed. Okay, so this is a model. What model in the sense, like I am pushing my model like a Falcon, 1 billion parameters, LoRa adapters, 4-bit Gen English. Gen English in the sense like it's general English. That's what we have trained on. I'm pushing this model. So now you can ask me, okay, sir, now you are saying that you are having the LoRa adapters. Now, now we need to merge them, right? Okay, so now your question may have this question in your mind. So okay, so now you generated only the LoRa weights. Okay, now you have to merge with the actual model, then only it will become as a model. Wait, no sir, but you are not merging with the actual model here, but instead you have pushed it. It doesn't make sense, right? Of course, this is your if you have this question, you're in a good track. So that means I'm just pushing my adapters, now you are coming into the game. Okay, now I'm telling, I'm marketing it. Now I push to my model, now I fine tune to my model with the GK data which Falcon is not aware of previously. Now you are working on the same project, now you are working on another project, now you wanted to use that. Okay, you also have a similar requirement as like me. At the time you will be searching in Hugging Face and you are finding, okay, there is a person called Jai Ganesh and he pushed some LoRa adapters in such a way. Now what you will be doing, now what you will be doing you will be taking a Falcon model. Okay, you will be downloading a Falcon model from a Hugging Face, and you will be downloading my adapter also. Okay, now you'll be downloading my adapter. Okay, now what you can do by using this one, this is your new model. Okay, now this is your new model, and this is your trainer new model. Now you are merging them. Okay, now you can able to see that merging places or merge function, where it is merging and download. So you are taking the base model, that is a Falcon model, and you will be having my new model, that means my new model, right? This is my new model, and you are merging them together. Once you're merging them together, you will be having like a actual model. This is a model which is trained on your data and as well as actual Falcon model. Now you hope you can understand what I'm trying to say. Okay, now this is all about adapters. So now this is all about an adapters. Where is it? Like this is adapter actually I'm pushing into my Hugging Face hub. So instead of merging, you can ask me, okay sir, you have done this much of job, why are not you merging this model, why are not you merging this model and pushing into Hugging Face hub, sir? Think about it. Your Falcon model is a 1 billion parameters, a huge model now. Okay, now if I'm merging with on top of my parameters, of course, like it will be like 8 GB in the sense, additionally it will be 808 8.5 GB it will be converted into. If I'm pushing into Hugging Face, of course it's not helpful, because what is actually helpful, that adapters is helpful. What you learned, that adapter is helpful. Already you know deep learning and everything. Now you don't need to buy a book deep learning with the LLM. You can just buy LLM, and you can combine these two knowledges and you can study about. That's what I'm telling here. Okay, I'm just making adapters ready. My adapters I'm pushing into the model, I'm pushing into the source, the common community, and whoever wishes to use that source code, let them use it and then let them use code. I instead, if I'm pushing this model, think about it. Now, what I have to do in the sense, if I merge and if I upload in the sense, each and every time you need to download this model. You have to keep a dependency of my model. But if I have an adapter, anybody can use it. So now can you show some examples are related to this? Any adapters is related to? You can find some LoRa adapters, some of the models. Here you can see this is a model. So now I have uploaded LoRa model, right? That is maximum like a 50 MB or 100 MB. Maximum it's a 50 MB, 100 MB. This is a some user like a, this is a LoRa Q1 image example. Somebody uploaded their LoRa model. Okay, so this is all about, you can able to see there is no parameters or something. This is like a parameter, this is like an adapter, like how I have uploaded into the model, right? The similar way. So now you can have other thought. Okay sir, this is evaluating the LMs. You might have experienced this blue and rouge and all, you already walked through this one. So I have blue and rouge examples also I have posted here. So what is a blue metric and everything? So you know what is a blue metric and what is that rouge metric and all, right? That and all I have used here, so I don't want to walk through this one. This will take some additional time of us. Okay, instead directly I'm going for understanding the parameters now. Okay Jay, now you fine tune, you have taken a Falcon model, now you fine tuned a very fewer amount of a Falcon parameters. How amount of parameters you have changed, Jay? Can you explain that one? Yes, I have a method here. So this method is like a trainable parameters. Okay, so this is, I'm keeping it as a two variable. I'm taking my actual model and the named parameters is the model which we have updated with respect to the required gradients. Okay, now here you can see the total trainable parameters. Okay, trainable parameters is like a 1 lakh 15 lakh 72,000 sorry 15 lakh 72,864. Okay, this is a parameter I have updated, but what is the actual model parameter? This is all about like a 709,218 what is that, 304. So that means like 70 crores 92 lakhs 18,000 parameters. Okay, your Falcon 1B overall parameters is all about like a 70 crores 92 lakhs 18,000 parameters, and out of this 70 crore I have just updated a 15 lakh of parameter. That means it's close to 22%. That means 0.22%. You get it right. So what it try exactly says, like this is the overall parameters of frozen plus trainable parameters, the overall adapters, and this is how the overall made is. So the actually proportional device you're updating approximate 1 in 451 weights actually. So if you're taking a 451 weights, I'm just updating only one instead of a fully fine tuning. We fine tune just 1.5 million parameters. This is the overall model fine tuning is all about. Okay, so this is how your model is updating with the fine-tuned parameters, with the complex structure, with the complex knowledge which is already holds. So now you can run this code. Actually it will run for sure because it's run by before only I ran it, it will run. And but when you are running this one, you have to give your name actually. So you have to, for example, if you have a Hugging Face account, you have the profile name, right? This profile name you have to give this Jayish ID, right? This ID, if you have some ID that you have to give. For example, if your ID is like a professor AXB, something else, in the sense you have to give the ID right here in order to push, or else it will not push your changes to Hugging Face Hub. So that one you have to do, and the rest everything will run. And also you may face an error when you are running this model, because merging adapters with respect to your older model is not easy. Okay, maybe you will face some error when you are executing this, but this is not required so far, because this is just I have added for knowledge purpose. This I just added for knowledge purpose. All we need to know about is like how to fine tune our model and how to utilize those LoRa adapters on going forward. Okay, so now when I'm explaining the code, I was explaining almost for half an hour, right, the coding code. But altogether, if you say I'm taking my data set, okay, this is my load. I'm loading a model. I mean the quantized model. So instead of 16-bit, I'm loading like a 4-bit. That's it. I'm LoRa configuration, setting the LoRa configuration, tokenizing my input data. That's it. Next, and training arguments. I'm defining my water law, how I wanted to make my model to train. Next one is a data collator, how I wanted to handle my data, how I wanted to keep my data. So padded data, tokenized data, and how my model wanted to get trained off. That everything I'm just giving it here. Okay, now ideology, that ideology I'm giving it to the trainer argument. I'm training my model. That's it. Maximum 60. Maximum 60. Okay, and if you run it and you will not have a good results, the reason is nothing but because I have a less epoch and I have a very less learning rate. You can make it as a 0.0001, maybe you can convert in such a way. And also you can increase a low rank adapter, like you can increase it to 16 and you can make it as a 32. Likewise you can increase that, and the dropout you can increase to 20% or 30% also you can increase. All I can say is like you have to change your data set. Okay, here my data set is a very less data set. Now you can take your own data set and you can try to fine tune your data or your model, so that you can able to experience some amount of quantified information, so quantified knowledge of how your models actually reacts for your questions. Okay, it's okay. It's this is more likely a fine tuning, and another fine tuning is here. But anyway, I'll give that source code to you. Maybe you can take a look at it. That's a simple one. This is nothing but this is a one. I'm taking a BERT model and I'm fine tuning my model with the classification model. I'm making this a generation. Actually, this is like it's a language model, but I'm fine tuning this language model as a classification model. Fine tuning for the classification problem statement. Okay, so you can take this source code also. Maybe you can have a take a look at it and you can learn from your end. Okay, so any queries from your end to be asked, please. I'm going for a Q&A now. The questions are welcome.
Questions from the participant? Participants, if you have any questions, please post your questions in the chat box, or otherwise you can even raise your hands. No questions. Okay. So if there is no questions, we will conclude, Jay. Thank you so much
Yes,
for
ma'am.
delivering such an insightful and engaging session. Your presentation was truly exceptional, Pam, and demonstrated remarkable
Thank you,
depth
ma'am.
and clarity. Jay clearly
Thank you,
delivered
ma'am.
a detailed and advanced session on fine-tuning large language models, focusing on practical techniques and challenges He began by introducing Hugging Face platform and its vast collection of pre-trained models such as Distilbirds, Roberta, Falcon, and Llama, which can be customized by various LLP tasks like text classification, question answering. The core of the session emphasized fine-tuning strategies, including full fine-tuning, LoRa, and QLoRa. Full fine-tuning involves updating all model parameters, which is resource intensive and prone to issues like catastrophic forgetting, where the model loses previously learned knowledge. LoRa addresses this by adjusting only a small set of adapter layers, preserving the base model's knowledge while enabling domain-specific learning. Additionally, the talk covered types of fine-tuning, including domain-specific, task-specific, and three key techniques such as instruction fine-tuning, chain of thought fine-tuning, and multitask fine-tuning. The session effectively bridged the foundational theory with hands-on implementation, providing valuable insights for applying LLMs to customize real-world use cases. So he also explained how to fine-tune the parameters with this set of codes. Hope the participants also have enjoyed the session. Thank you so much, Jay, for this wonderful session.
Yeah, thanks a lot, ma'am. Thanks a lot
Thank
to
you.
me. Yes, thank you, ma'am. Thank you so much. Thank you so much for all the
I would like
participants.
to thank you, Jai Ganesh sir. And there is one more information, participants. That link for your feedback has been given in your chat box. The same will be communicated in WhatsApp also. And tomorrow we have our end session. So tomorrow your session starts by 2 o'clock afternoon, and you will be having three sections by three resource person. Following that, you will be having an online test where you will be circulated with the Google form for giving your test to be taken. And the conclusion of the FTP will happen as a validatory function from 7:30 to 8 o'clock. So I would request you all to kindly join for the session on time, and then we'll let us have a happy learning process. And one more thing, the Google, the feedback form come attendance form which was shared today will be enabled till 10 p.m. today. Thank you all. And
It's
Jai
as
sir,
instructed by
Yeah,
one
ma'am.
Anita ma'am. Participants kindly join from 2 p.m. onwards tomorrow. That is mandatory. And you're also supposed to write the quiz. Separate test part will be conducted and then followed by the valedictory session. Yes, ma'am, please proceed.
Yes, madam. There is one person who raised their hand, Pooja or something. Is there anybody having any queries? Sir, somebody raised their hand. Kirti
Yes, ma'am.
Priyan. Kirti Priyan, sir,
Yes.
kindly
Yes,
go ahead.
please, ma'am.
Yes.
Ma'am, you'll be sharing
Ma'am,
the PPTs and so on in a Google Drive, the recordings.
Recordings. Yes, sir, we will be sharing you the recordings. Recorded SharePoint link we will be sharing you.
Thank you,
All
ma'am.
will happen only at the end of the FTP, sir.
Ma'am, it will be helpful if you can share today because we'll be able to rehearse at least for the test.
Okay.
Sir,
Yes,
tomorrow also you
we will
have
try.
sessions, sir. I will try
Correct,
our
ma'am, but
best.
if you can at least send us, we'll be able to recollect some of the points.
Sir, some people we have yet to get the PPTs that we are waiting for. Recordings you can get it. Recordings
Yeah,
we will share you.
yes, yeah,
Okay, sir.
something,
Leave it.
if we can have.
Yes,
Yeah,
sir. As
yeah.
you said, we will try our best to share. Don't worry.
Mm.
Thank you, ma'am. Thank you so much.
Yes.
Meena ma'am. Meena ma'am
Yes,
has
ma'am. Good
raised her
evening,
hand.
ma'am. Ma'am, tomorrow at what time the session starts? At 2 p.m.?
Yes,
Yes,
madam.
ma'am. 2
2
p.m.
p.m.
2 p.m. Then at what time we'll be having that mock test?
Possibly by 6 o'clock, 5:30 to 6:30, you will be having
Okay.
one more session. So by 6:30 to 7:30, you have your online test. Then 7:30 to 8 will be the validatory session.
Okay. Actually, tomorrow I have college. I'll be in traveling. That's why I wanted to check with the timing of mock test. At what time it
Uh,
will be?
Sometime back itself, I have shared this schedule in our WhatsApp group. I will share
Okay.
it once again.
You can
Yeah. Okay,
check that
ma'am.
schedule, ma'am.
Okay, ma'am. Okay, ma'am. I'll check with that,
Mm.
ma'am. Thank you, ma'am.
Yes,
Okay.
thank. Just thank you all.
Okay. Any query? If you have any queries, otherwise we will conclude the session. Kirtiparian sir, again you raised your hand. Any queries?
Good evening, ma'am. Ma'am, I
Oh, sorry,
think
ma'am.
you said the link has been shared through WhatsApp and the schedule as well. Ma'am, could you please pin it in the group because I
Our
think
scheduler in WhatsApp group, I will pin it, ma'am.
Yes,
yes, ma'am.
ma'am, we'll
And
do that.
ma'am, yes, ma'am. So, ma'am, because the chat in the chat section as well, I'm not able to see the link. So I just wanted to confirm if it's actually shared or like it will
Today,
be
ma'am.
shared.
Today chat. Today I haven't given it in WhatsApp so far. Once this recording done, I will be pushing it in the WhatsApp also.
Okay.
Yes, I'll
Okay.
be sharing
It's not in the Teams
WhatsApp.
chat as well, right?
No, ma'am.
Yeah, understood, understood. Yes, ma'am. Yes, ma'am.
Okay,
I'm
okay,
sharing now. Okay.
okay, okay. Thank you.
Mm, Shared.
Yes, ma'am. Shall we wind up the meeting?
Yes, madam. Hope that
Thank
everybody
you.
have got clarified.
Thank you all. We'll meet tomorrow at 2 p.m.
Thank you all. With all you, ma'am, recording you can stop, madam.
Yes, ma'am. Yes, ma'am. Yes, done. Thank you.
Okay. Okay. With all your permission.